Second.
I confirm that. I just got a message that said it's being live streamed now.
Okay.
Yep, I think we are live now. Yep. Welcome, viewers. Welcome to another episode of Let's Talk Science. And in this episode, we have an interesting astrophysicist as our guest, a very special guest, Dr. Guha Thakurta. He is joining us from California. And also with me on the co-panel, Mr. Teja Begari from Hyderabad and Amol Mane, astrophotographer, joining us from Sydney, Australia. Welcome, everyone.
Thank you.
Thanks.
And this episode is supported by Science for Society, Indian Humanists, and Babu Gognani Humanists and Rationalists Arena Facebook group. So before moving into the show, let me introduce Mr. Guha Thakurta. So he's a professor, astronomer, and department chair from Department of Astronomy and Astrophysics from University of California, Santa Cruz. He has a BSc from a degree from St. Xavier's College and a PhD from Princeton University. His main research is around the formation and evolution of galaxies, specifically their accretion, cannibalism, history, and dark matter content, chemical enrichment, and star formation history, and many more things related to galaxies. So today we can get a little more details and knowledge and his opinions and experience in astrophysics and astronomy. Welcome to the show, sir.
Thank you very much, Prasad.
Yeah. So we can start with one interesting question that I have personally. So what is going to be the future for our Milky Way galaxy and the nearby Andromeda galaxy? And what is the most interesting research or answer you're looking for in terms of the interaction of our galaxy with the nearby Andromeda galaxy?
So really depends on how far in the future. When we human beings think about the future, we often think in terms of years, months, days, weeks, decades sometimes. We rarely think in terms of centuries because we're not going to be alive then. It doesn't matter to us what the future will be. Our loved ones will be alive, but not ourselves. So there'll be very little change in the history or in the future of the Andromeda and Milky Way galaxies on those kinds of timescales. But if we allow ourselves to think in terms of billions of years, one followed by 9 zeros now, not 2 zeros, then on the time scale of a few billion years, 3, 4, 7, over that time scale, the Andromeda galaxy and the Milky Way galaxy are likely to merge and become a single galaxy where there are 2 now. And I say, 3, 4, 7, not because there is great uncertainty about when it's going to happen, but I give you a range of numbers because the merger between 2 galaxies is not an instantaneous process. It takes a few billion years to unfold. So it'll start 3 or 4 billion years from now, but the 2 galaxies wouldn't have completely merged into one for several 3 to 4 billion years after the start of the process. Now, what is the most interesting thing? I think the collision or merger between Andromeda and the Milky Way will have very little effect on the solar system and things like that. There'll be other things that will affect the solar system, like the sun becoming a red giant. That will be, the thing that will be a more definite threat to life as we know it on this planet. I'm very interested in the structure of galaxies, our galaxy and Andromeda. There's a 250-year-old idea, goes back to Immanuel Kant, philosopher, about galaxies being island universes. And when we think about islands, when we think about the Andaman Islands, or if we think about Sri Lanka, the island, there is a body of water between an island and the person who describes it as an island from the outside, okay? Or between two islands, there's bodies of water that separate them. I'm interested in the question of whether galaxies are truly islands or not, because we are finding that the extent of the Milky Way is so great, and the extent of Andromeda is so great, that perhaps they're not islands after all. Perhaps they're overlapping, actually. This is something I'm very interested in right now, to answer your second question.
Yeah, that's very interesting. Given the vastness of just not the space, but also our galaxy being 100,000 light years across, depending on where we draw the boundaries, it's very interesting and curious at the same time to know the eventual fate of two galaxies that are going to merge. And I'm sure there are many more examples we would have already known elsewhere, not just in the immediate cluster where we are in. So when you said there is no threat for a star system like solar system from the merger itself, from a grand scale, like when two galaxies merge, so what is the result going to be? Is it going to be one big galaxy at the end, and will it still have some effect like the bigger one, still retaining the direction and the spin that it has before the collision, something like that?
That's a very good question. The result is one big galaxy. But when we think about spin, our galaxy is shaped like a frisbee, shaped like a disk. So is Andromeda. That configuration is almost certain to be lost. We're not going to be like spinning disks after the collision. It'll be more like a swarm of bees around a beehive, where every star is orbiting. But in general, one star's orbit is not aligned with another star's orbit, unlike a frisbee, where all the stars are orbiting in a plane and they're all going around in the same sense. That is very likely to be changed. That, in fact, is going to be the main change during this merger process between the Milky Way and Andromeda. When you have two galaxies that are comparable in size and mass, even more important, then they tend to do a great deal of damage to each other, in terms of their shape and form, not damage in terms of stars colliding into each other.
Yeah. So in fact, I heard that the chance of two stars colliding each other from different galaxies is very minimal.
It's very small. It's very, very
okay.
small. And a good way to think about why is to think about the scale of the problem. If you took the sun, and if you were to shrink the sun down to the size of a small marble, a glass marble that you can hold in your hand, 1 centimeter diameter marble, if you were to do that, if you do that proportionately to all stars in our Milky Way, stars that are bigger than the sun will be more than 1 centimeter in diameter. Stars that are smaller will be less than 1 centimeter. If you do this proportionally, including the distances between stars, if you kept that proportional as well, stars are like 1 centimeter marbles separated by typical distances of 300 kilometers. So if you put a marble down and you say, in my home, this is my sun, think about a town that's 300 kilometers away. The next star is typically that far away. Yep. You can see why, even if those marbles were swirling around for 1 billion years, the chances of them coming close to each other and creating anything, a meaningful gravitational interaction, are very, very small. Now, of course, that's for a star-star interaction. This is even true if you consider a star's planetary system. The planetary system is bigger, of course. Our planetary system is much bigger than the diameter of the sun. The sun's light travel time across the sun is a few seconds. It takes a few seconds for light to travel. The length, the diameter of the sun corresponds to a few light seconds, couple light seconds. Actual photons take much longer to travel to the sun because the sun is very opaque. But in terms of diameter, if you take the diameter and if light could travel in a straight line, it would take a few seconds. By contrast, the solar system is about a light day in diameter, several light hours, comparable to a light day. Even so, the distance between stars is light years, not day, several light years. So even outer solar system planets, which are the most susceptible to interaction with other stars, are very unlikely to get affected. The sun is relatively protected. It's only 500 seconds of light travel time from the sun. And compare that to 4 light years to the nearest star. 500 seconds versus 4 years. That's the ratio of distances. The chances of that star affecting our sun are very small compared to the sun's influence on us. I'm not saying the effect is zero, but it's negligible compared to the sun's gravity.
Yeah,
sorry, I'm throwing all these numbers at you.
Yeah, so it's amazing how incomprehensible most of the astronomical things are when it comes to the vastness of space. Starting with human mind, it's not easy for us to understand these big numbers. I think that's why they are called astronomical numbers, the big numbers, 10s to the power of 20s and 23. So I think Amol has a few questions as well. Amol, you can start.
There's something fascinating that you mentioned, which is about galaxies not really being island universes, but somehow being connected. That's a very fascinating concept. I believe it sort of come out recently in the last maybe few years or so.
Right.
And we're trying to see, it seems that there's some kind of a intergalactic cosmic web that seems to be binding these galaxies. There's also the mysterious sort of dark matter. Are these two connected? Is it the dark matter that seems to be binding the galaxies? If you can elaborate on that, sir.
Yes, indeed. One of the big advances in understanding cosmology has been telescopes, of course, the power of telescopes, technology of telescopes. But a well-hidden secret about advances in astronomy, a well-hidden secret is the fact that computing power has grown by Moore's law, as you know. Computation has made huge advances in our understanding of astronomy, just like technological advances applied to telescopes has resulted in huge advances. And detailed computer simulations that start with conditions in the early universe and advance them forward in time, tracking the effects of gravity, tracking the effects of hydrodynamical forces, those suggest that indeed the universe, the structure of the universe should be something like a web. It's called the cosmic web. We're used to the World Wide Web, but the cosmic web is much bigger. But it's this web-like structure that is indeed a mix of dark matter, mostly dark matter, but also so-called baryons, which is the normal elements in the periodic table that we know and love, that we understand, that makes chemistry a difficult subject. Yeah. The cosmic web is made up of both of these things, ordinary matter as well as dark matter. The gravity of dark matter is the dominant gravity. There's very little, as a fraction, the gravity of ordinary matter is quite small compared to the gravity of dark matter. But the cosmic web is indeed what seems to be the connecting things between galaxies. And I just want to be clear that it's not like galaxies have sharp edges. People never thought they have sharp edges, but so their density falls off with increasing distance from the center. And the question is, what is the rate at which it falls off? How far does it fall off like that before there's an even sharper cut? So people call this the density profile radial density profile of a galaxy. And that's a plot where the density of stars is on the y-axis. On the x-axis is distance from the center. What does that shape look like? Computer simulations suggest something, but I'm very interested in making measurements of this for our galaxy, Andromeda, and other galaxies. You said something very important about astronomical sizes being incomprehensible. I think we'll get to this possibly later, but I think they're not completely incomprehensible. They do stretch our imagination. They stretch us to think beyond our everyday experience of what we encounter here on Earth, the distances and times we encounter during our lifetimes here on Earth. But I think it makes us, we are sentient beings. We human beings are sentient beings. It sharpens our senses to be able to think about things that are so much bigger than our everyday experience. I think it's important because of that.
Yep. Thank you, sir. Teja, do you have any questions? You can start.
Yes, I have a couple of questions. First question is going to be about the shape of the universe. What do you think is the shape of the universe? I mean, like as
And
you
Teja,
said,
you mean shape of the universe, not shape of galaxies, right? I just want to be clear.
shape of the universe and not shape of the galaxy.
That's a good question to which I don't have an answer. There's speculation as to whether our universe has boundaries or not. Because when something is infinite, then we can't really think about its shape, right? Because when you think about let's say you're thinking about the shape of a football. It's shaped like a sphere. If you're at the center of that sphere, you can say that the edge of that football is equidistant from you in all directions. If that were the case for our universe, the edge of the universe were equidistant from us in all directions, then we would call that the shape of our universe, a sphere. If the universe has no edge, you can see that defining the shape becomes difficult. But I'm going to answer your question in a particular way and say that if I can change one word in your question, if I can add one word to your question, then I can answer your question. If I can put the word observable before universe, if I can say what is the shape of the observable universe, then I can be much more definite with my answer. That is indeed a sphere whose radius is 13.7 billion light years. That's how long it's been since the Big Bang. So everything we sense today comes from a sphere that we are centered on. It's our observable universe. That's why we are centered on it. We're not at the center of the universe. We're at the center of our observable universe. And everything that we can sense comes from a sphere whose radius is 13.7 billion light years. I tricked you by adding a word and answering your question. I hope that, does that help?
Yeah, it does work. So as we also got to know about the shape of the galaxies, I mean, could you also let us know something about the different shapes of galaxies and like say we have elliptical galaxies and spiral galaxies. So are these the only type of galaxies, or say the irregular galaxies? Are there different types of galaxies with the different characteristics? So could you let us know them?
Yeah, the three you named, which are disk galaxies or spiral galaxies, elliptical galaxies, and irregular galaxies, are indeed thought to be the main classes of galaxies. These are called morphological classes. Morphology means the form of a galaxy. So if you want to name a galaxy by its appearance, in human society, we're taught not to judge a person by their appearance. Don't judge a book by its cover. But somehow, for galaxies, it helps us to understand the physics of their formation if we can classify them according to appearance. And this is one person who made this kind of study famous. Many people have done these sorts of studies, but one person who really made this very famous is Edwin Hubble. Edwin Hubble wrote a book in 1929 called The Realm of the Nebulae. And the word nebula means a cloud, but he was really referring to clouds of light that what we're calling galaxies. So yes, it's really those forms, the elliptical galaxies, spiral galaxies or disk galaxies, and irregular galaxies. In general, there are many more small galaxies than there are big ones. That's true of almost everything in the universe. There are many grains of sand on a given beach than there are boulders. But in general, there are many small galaxies compared to big galaxies. And if you think about the fragmentation process, if you have a big cloud that fragments, or if you take a big rock and you take a sledgehammer to it, there'll be a few big pieces, few big fragments, but there'll be many small fragments. So small galaxies outnumber big ones. Small galaxies come in different types. You can have mini elliptical galaxies that are called dwarf ellipticals or dwarf spheroidals. And you also have star-forming irregular galaxies. Big galaxies tend to be spiral or elliptical. You don't get very large irregular galaxies, not in the present day. Maybe a long time ago in the universe there were that. But more galaxies are spiral than elliptical. So frisbee-shaped galaxies are more common in the universe. And the reason they're frisbee-shaped has to do with their angular momentum, their spin rate. If you've been into a kitchen where they make pizzas, you can see that the person takes dough and spins it. And that gives it its flat shape. The angular momentum causes things to spread out or causes it to take on that configuration. Does that answer your question, Teja?
Yes, sir. And because we also spoke about elliptical galaxies, it is said that elliptical galaxies are the oldest galaxies. And why is that said so? I mean, we hear people saying elliptical galaxies are the old galaxies.
Yeah, one has to be a little careful when one talks about age here, okay? Because you can measure a galaxy's age in more than one way. Okay, and this may not be so obvious. So let me explain what I mean by that. Every star in a galaxy has an age, right? So every star was born at some time. And so you can measure a galaxy's age by asking how long ago did the stars form, each individual star form. You can take the average of those and say this is the mean age of the galaxy. That's one way of measuring age. Another way of measuring age is to ask how long ago did it come to its present form? If it had a very different looking form, same stars, but if they were distributed differently in the past, then the assembly history or the assembly age, the time at which it was assembled into its present form, is a completely different way to define a galaxy's age. And in particular, when material gets assembled, if something got assembled and stars formed during the assembly process or after the assembly process, then the assembly age is older than the stellar age on average. And if it were the other way around, if mini galaxies formed and the stars in them already formed and came together, merged to form an elliptical, then the stellar age is older than the assembly age. And for elliptical galaxies, it tends to be that the stellar age is very old. The assembly age may not be as old as the stellar age. Does that make sense? That's two different ways of measuring age that are both valid.
Right. So there's also a few questions about variable stars, because that's one of your area of expertise. So we know that these variables change their magnitude per time intervals. Talking more about the standard candles, the first standard candles, the Cepheid variables. Why do the Cepheid variables pulsate? I mean, why do the stars?
Why do stars pulsate at all? Yeah. A good way to think about it is, we're all familiar with pendulums. If you have a static pendulum, it represents a balance, a static balance between the tension of the wire that's pulling on the bob, the pendulum, the weight on the pendulum, and the force of gravity that's pulling the the ball of the pendulum downwards. Okay, so the tension of the wire is pulling it up, gravity is pulling it down. If you have a static pendulum, that's a static balance between these two forces. But you could also have a swinging pendulum where the position of the pendulum is changing and it's repeating its motion, but nothing is running away. It's a cyclical motion. It's going back and forth, it's repeating its motion. If there's no friction, it will keep doing this for a long time. I'm using that as an analogy because stars represent a balance not between the tension of the wire and the force of gravity of the Earth, but a different kind of balance. The star has its own gravity that's trying to make the gas ball that's a star contract. Its own gravity is trying to bring everything in. That's what gravity does. It tries to make things, pull things in. The nuclear fusion that's powering the star, the thing that makes the star shine, central part is undergoing nuclear fusion reaction, that generates a lot of energy. And we know that nuclear fusion can lead to an explosion. That's what we call a hydrogen bomb, for example. It's powered by the fusion of hydrogen. A star represents, you can think of a star as a static hydrogen bomb, where the outward explosive force, normally explosive force of nuclear fusion, is exactly balanced by its intense inward gravity. Most stars, for most of their lifetimes, achieve a static balance. The sun is in static balance. It's going to stay this way for another 5 billion years. It's already been this way for about 4.5 billion years. But at certain times, certain stars go through phases where they go through an instability phase in the Hertzsprung-Russell diagram, in the diagram of luminosity versus temperature of a star. If a star crosses into certain parts of luminosity versus temperature space, they go through a phase when they're in dynamical balance, not static balance, where they're pulsing. When they're going outwards, nuclear fusion is winning temporarily, and when they're contracting, gravity is winning temporarily. But it's a dynamic balance, just like a swinging pendulum. That's what a variable star is, like a Cepheid. I study Lyrae, which is a different class of variable stars. The sun is not going to become an Lyrae star, but other stars that are sort of close cousins of the sun, similar mass, but just lower in chemical composition, are likely to become Lyrae kind of variables. Lyrae are a different kind of standard candle than Cepheids.
Right.
Sorry if my answers are, please tell me if my answers are too long and if I should be trimming it down.
Nothing as such, so you can go ahead with the answer. There's also a few questions from the audience we're getting. Vaibhav Nellore asks, what's there before Big Bang and what could have triggered Big Bang? That's the question.
It's a great question. I don't think the answer is very well established. At the end of the day, astronomy is a branch of physics, and observational astronomy is a branch of experimental physics. You make measurements of the universe, you build a theory that explains those observations. We can't make direct observations of conditions before the Big Bang. Because of that, it's difficult to build a theory that follows the usual logic of physics, where you make observational, you make experimental measurements, you make predictions, and build a theory around that. That's a long way of saying the language of physics doesn't offer an easy answer to the question of what happened before the Big Bang. That hasn't stopped people from thinking about the possibility that our universe is one of many systems, right there is an apparent contradiction. When we say universe, uni means one. There's a notion of a multiverse where there are other entities that are like our universe that are happening at different points in space and time. There's been a lot written, a lot speculated about multiverses. It's also was originally called chaotic inflation. It's more popularly known as multiverse today. The names I associated with things like this are Andre Linde, Alan Guth, my colleague Anthony Aguirre at the University of California, Santa Cruz in the physics department. These are some of the people who've thought about the multiverse, and that's the closest I can. I mean, I don't want to. This is the limit of what I understand about this question.
So there's also another question from Sambasivara Mutyala. So Mr. Mutyala asks, please explain how matter is formed out of energy with examples.
Yeah. So this goes to Einstein's special relativity, a theory that was developed in 1905. Einstein found that in order to build a self-consistent theory that explains motion that is close to the speed of light, very high speeds, V over C approaching unity, not greater than unity, but approaching unity, values of 0.8, 0.9. If you want to explain the motion of things and you want to understand how observations of the universe around us fit into that theory, a natural product of that theory is the famous formula E equals mc squared, where E is energy, m is mass, c squared is the speed of light squared. What I would say, this formula, which is arguably the most famous physics formula of all, is a natural consequence of Einstein. The equivalence of mass and energy is a natural consequence of Einstein's special theory of relativity, a theory that's designed to explain speeds close to the speed of light. That doesn't exactly answer the question of how is mass converted to energy. Ultimately, special relativity, like many theories in physics, is a mathematical theory, and one has to really work through the mathematics of it and understand that why E equals mc squared comes about. It comes about now. It's not a general relativistic principle, it's a special relativistic principle. E equals mc squared. Was there a second part to the question, or was that the... Oh, are there examples? Are there examples? We see many examples in the laboratory where two photons are packets of energy, where two photons can come together and disappear. And in their place are two particles, a particle and its antimatter components, a proton and an antiproton, electron and a positron. So that's called pair creation, where from energy you're creating matter. And the opposite is also seen extensively in the lab. That is a particle and its antimatter particle, electron, positron, proton, antiproton, neutron, antineutron, can come together. The particles will disappear, and what's left in their place are two photons. So that's conversion of mass to energy. This is indeed seen and studied extensively in a laboratory. So E equals mc squared. It's been experimentally verified many times over. To answer the second part of the question.
Yeah. With that, we answered all of the questions from the audience.
There's another question from Shiv Shankar. Are there any stars outside the galaxies?
Yeah, it's a great question. There are. You can think of them as orphans. They've been flung out of stars, and there are certain processes that can fling them out of stars. One thing, if a star strays too close to the central black hole, it can be catapulted out. There are these things called high velocity stars, HVS, high velocity stars. Many of them are thought to have been catapulted by black holes at the centers of galaxies. A few years ago, I worked with a group of astronomers where we were studying explosions in stars. And we were interested to see that many of these explosions that we were studying were happening outside galaxies, well outside galaxies. So those explosions were exploding stars. So even though the stars were too faint to see before the explosion, the fact that the explosions were happening outside the galaxy told us that these stars exist. Only a small fraction of them explode, but there must be others that are not exploding that must be there. This was a paper with someone named Avishai Galyam. He was the lead author. And this was a paper on intergalactic supernovae in the, I believe it was in the Virgo cluster of galaxies. Now, the way stars make it outside galaxies is not just through catapulting around black holes. When two galaxies merge, not all stars make it into the merger product. Some stars get orphaned in that process.
Thank you for that. Amol, do you have any other question?
Okay, I have a question about the dark matter. So we understand that dark matter was required to explain the unknown sort of source of gravity that's required to bind the stars at the outer layers of galaxies, and also to bind galaxies moving in local clusters. And subsequently, there has been some evidence suggesting dark matter acting as gravitational lenses of very far off quasars and galaxies. But we haven't really detected, so it seems we still call it dark matter, right? So it's still a mystery. So it's not completely resolved as to what these would be made up of. And I understand there's research being done to identify what particles they would be. They could be weakly interacting massive particles on that. And so I understand, I was reading about it a bit briefly, and I understand there's a research done in Italy. So that detector, I think it's called the Dama Libra detector, is the only one which seems to seasonally detect these apparently what seems to be dark matter, and there isn't anything that's not confirmed by any other detector in the world. So there's a plan to, in fact, there's a detector being built in Australia, so to rule out the seasonal effect of that detection. It's a place in rural. It's a gold mine, in fact, in state of Victoria in Australia. That's so. My question to you, sir, is so do you see what would be a conclusive proof, something similar to the gravitational wave detection of LIGO, that you can conclusively say that this is the foundation of a dark matter? What would be particles look like? Would they be particles, or would they be maybe something that we haven't understood about gravity itself, or then alternate theory being the modified Newtonian dynamics?
Yeah, these are great questions, Amol. My personal sense, talking to my colleagues and from going to conferences, hearing people speak, is there's not a lot of support for modified Newtonian dynamics. Think that gravity behaves differently. It was an interesting idea, but it made certain predictions that have not been borne out. And so I think it's fair to say that most physicists and astronomers believe that there is matter out there. It's not just us not understanding how gravity works. The gravitation, it's not a modification of how gravity works on large scales. Certain kinds of dark matter appear to have been ruled out, at least on galaxy scales. We don't think the dark matter is made up of substantial mass black holes. I was part of a paper recently that said that there's certain, if they're really small black holes, asteroid mass black holes, you can't quite rule that out. This was a paper led by Nolan Smith, a graduate student in the physics department. It refuted a previous claim that said, oh, dark matter cannot be made up of asteroid mass particles, and this showed that no, it can.
Okay, so these are not primordial black holes. These are
these would be primordial asteroid mass black holes, was the thing that Nolan's paper said is not ruled out as a possibility. In general, we don't think what is ruled out is the possibility that the dark matter is made up of solar mass black holes or anything more massive than that. We know that it's unlikely to be made up of dead stars. Like the Macho project was, again, was an experiment that had a very specific model that made specific predictions, and they were not borne out by observations, so marchers were ruled out. Similarly, WIMPs come with specific predictions. There are different flavors of WIMPs. They come with specific predictions for how often they should interact, what that should do. So to answer your question, how will we be sure? It's if we can, if there are promising models for dark matter, which there are, as some get ruled out and others get, or one gets confirmed in terms of what it predicts for the interaction pattern of dark matter particles or WIMPs, that would be, I think, the way it would go from theory to accepted fact. The pattern of interactions in these detectors. The Large Hadron Collider, LHC, is also, in general, dark matter searches are happening with some large intensity of effort.
So would the LHT be able to perhaps detect some of these massive particles, maybe with larger energy? Is that what would be required, perhaps?
This is a topic I haven't followed very closely, but depending on which kind of dark matter particle, I believe the LHC will have useful things to say about dark matter. But again, like I say, I haven't followed this particularly closely.
Yep. So I have a question. Normally, when we hear about astrology or major astronomical events happening, it's common that people from astrology, which is a bad sister of astronomy, if we can call that, astrologers, they come up and try to or pretend to predict certain events happening in for countries or in people's lives, saying that because um, uh, there is a chance of affecting people's lives, or whatever bullshit that they can talk about. So coming to the galaxies, do these galaxies also have some kind of effect on the other galaxies, not the gravitational forces, but if tomorrow they come and say, because of something happening at this galaxy, this is going to be the fate of certain people who are born into certain
Prasad, that's a good question. So there are many things rolled up in what you just said, many interesting things. So I grew up in India. I grew up in Kolkata, and astrology was never far away. It was as close as your nearest newspaper. Every newspaper had an astrology section. Right? So I grew up with astrology around me, but I managed to avoid studying it. Right? I never studied astrology as a subject. I don't know, therefore, what the logic is, if there is any logic, or how or what the goal. One thing is very clear. When I'm studying astronomy, which is something I did study compared to astrology, which I did not study, the goals are different. In astronomy, we're trying to understand the workings of stars, galaxies, things in space. Astrology's intention is human, is understanding effects on human life, not, it's a very different goal. I have, just to be fair, I've never studied the language of astrology, or, what the logical basis is, if there is a logical basis. So, it's not connected to physics, this much I know. It's not connected to the logic of physics anyway. This doesn't mean it doesn't use mathematics, it does, but it doesn't, not connected to the logic of physics as far as I understand it, astrology. To answer your question about galaxies, one very interesting thing that happens in galaxies, there are 4 kinds of forces in nature. There's the strong nuclear force, weak nuclear force, electromagnetism, and gravity. Gravity is different from the other three. In fact, Einstein says, don't even think about it as a force. General relativity is an alternate description of gravity. But one of the really cool things about gravity is there are no negative charges in gravity. There's no balance. Electromagnetism, you have, positive charges, negative charges, or North Pole, South Pole in magnetism. Because of this, these opposing charges, there's general cancellation of electrical and magnetic forces on the scale of a galaxy, or a scale between galaxies. Strong and weak nuclear forces, as their name suggests, only operate on the scale of a nucleus. They don't operate on large scales. So when you talk about galaxy to galaxy forces, really there are two options: electromagnetism, which is a long range force, and gravity, which is a long range force. Electricity and magnetism are, because of these presence of opposite charges, they cancel out on large scales. So you're only left with gravity, and that study of gravity of galaxies is indeed what we were talking about earlier. That brings in the notion of dark matter, etc. That's very well understood within the framework of physics. I say well understood with some reservation, because we don't know what the dark matter is made of. We just know how much there is. If it is there in that proportion, then we can explain the motion of galaxies quite well. We can, as you said, we can explain gravitational lensing, all within a coherent framework. That's a long answer to your question. I hope I didn't.
It's very clear. Yeah, it's very clear.
Thank you.
And again, another question that I have is, because we sometimes hear that there are courses being offered in some of the Indian universities on non-scientific studies or fields of not science, but like astrology and all. So because you have also studied both in India as well as in outside India, I think majorly in US. So from your experience and your opinion, what is the the Indian education system lacks or should adopt from other universities outside, like especially from US and the West, so that more and more youngsters are presented with opportunities in STEM research and astronomy and astronomical sciences in general, rather than just seeing science as another subject that can land us in a job, something like that.
Prasad, this is a question and topic that is very dear to my heart. This is very, very dear to my heart. I don't know where to start. I have there's many things I'd like to say about this. The first thing I'd like to say is I'm very interested in this notion of critical thinking. That is, thinking critically about something, evaluating evidence, understanding that someone who has studied something for 10 years understands that better than someone who studied it for 10 minutes. Okay. The notion of expertise, that I accept that there are people who are out there who are big experts on certain topics that I have no expertise in, and they should accept the same for me, that I have expertise in certain topics that as you know, looking around the world, especially in the last 10 years or so, not in any one country, the country I live in, that I've made my home, the US, in India, in Brazil, in Egypt, in Turkey, all over the world, I see an erosion in the importance given to critical thinking and expertise.
Absolutely.
Shouting loudly should not make me any more correct than someone who's whispering the truth, right? And we see this in the politics of the world around us, not in any one country, but literally around the world. I see erosion in critical thinking. We are having this conversation today during a time of COVID-19. COVID-19 is not behind us. It's still a pandemic that is taking lives, causing people to fall ill. I've had 5 deaths in my extended family in the last 2 years. So COVID-19 is something real for all of us. We've been affected by it. It's the biggest thing in our lives, right? I hope it's the biggest thing in our lives. I hope that there's nothing more drastic and negative than this horrible pandemic that we find ourselves in. There's a second pandemic that's going on that we can't see, just like the virus, something we can't see, and it's a killer that we can't see. There's a second pandemic that's going on that is even harder to detect, and that's this information pandemic, the erosion of critical thinking, the use of logic in our lives. I don't just mean in textbooks and science and exams, in our lives, in how we make decisions, whether it's about the environment, whether it's about people, whether it's about resources, economics. The erosion of critical thinking, the information pandemic, where someone can shout loudly or flood the web with information and really control the narrative, control people's decision making, is a very, very dangerous threat. In COVID-19, we start by vaccinating the oldest people and saying their health is at risk. In the information pandemic, we want to vaccinate the youngest people first. They're going to live with this disease the longest if we don't do that. I am deeply committed to spending the rest of my useful years getting more and more young people to see the value of critical thinking, not just in astronomy, but in whatever field they're interested in, whether it's athletics, sports of any kind, art, history, geography, everything involves critical thinking. And for them to follow their passion, whatever the subject is, but to see this through a lens of critical thinking is something I am deeply committed to. I think the world would be a much better place today if we adults, not the four of us here, not just the four of us here, but if all adults paid more attention to empirical evidence and thought critically about it. I'm sorry, I'm sounding like I'm standing on a podium and a soapbox and preaching. I'm preaching I'm talking to four believers here. I'm talking to myself and the three of you. We already believe this. That's what we're talking. That's why we're talking science. Let's talk the language of science more, is my plea to the viewers and anyone who cares to watch this.
Yep, very well said, sir. So that's what we resonate to, and Article 15A(h), I think, is of Constitution. We mentioned about the importance of scientific temperament and on critical thinking and humanism, promotion of humanism. So, Amol, do you have anything to add to this particular topic?
No, completely sort of agree to what Professor just said, and this is something I experience in the field of science when I'm trying to popularize science as an amateur astronomer. Because people get attracted to stargazing and astronomy because of the wonder, right? But there's a step beyond that. When you go into the science of it, you need to sort of inculcate this habit of critical thinking and systematically understanding what information is right and what is sort of misspread. So that element of critical thinking is required to make that jump into any science for that matter, or not even science, to just have a scientific temper for any approach in any approach in life.
And Amol, what you're saying is related to a particular fact. When I was a child, I don't know how old you are, but certainly when I was a child, the challenge was access to information. You had to go to a library, you have to find inside access to information. Now the challenge has changed. It's not access to information, it's access to quality information, access to accurate information. In fact, we live in a world where dilution is a problem. It was starvation before, and now we're drowning. We're drowning, and most of the things we're drowning in are incorrect, sometimes maliciously placed information to confuse or redirect us from a particular direction, right? We lived in an era of I grew up in an era of starvation, of not enough knowledge. Now we live in an era of flooding, drowning in knowledge, drowning in information, not knowledge, drowning in information, not quality information necessarily. And so it's become easier for people to control the narrative by, in this era we live in.
So given the situation, what in your opinion, do you think more and more scientists and science popularizers and people who believe and value evidence should become part of the mainstream politics, or people who can influence the decisions being taken at a larger scale?
That would be one way, but politics has become such a dirty word that no one wants to touch it. It's people associate that with a lot of negative things: power, corruption, not being nice to one another. We see that around. So that may be a way forward. The way forward I'm choosing is to involve young people in critical thinking in any way that we can. So I've started a program called Shadow the Scientists, where when I use a telescope, every time I use a telescope nowadays, I'm using my computer to control the telescope. I'm not turning a hand crank. I'm actually pressing buttons on a computer, this very computer that I'm connecting to you on Zoom. So what we do is the control software is on my computer. I'm controlling the telescope along with my students and collaborators. We give access through Zoom to children around the world, to teachers around the world, to other interested people around the world, to say, see how we do things. Just watch us do things. This is how scientists really work. I think if more people saw how critical thinking gets used in everyday life, maybe they would understand what it even means to think critically, how we solve problems. It's based on rationality. It's based on seeing the evidence out there, making a decision that's based on evidence, not based on opinion. So I think one of the dangers in the way I was educated and the way I see young people educated is we're often taught that problem solving is the way we solve problems in schools and colleges is we solve problems in an exam, right? Someone has set that exam. Some teacher has set that exam. That very fact that somebody has set the exam makes it unrealistic compared to problem solving in the real world. Nobody has set COVID-19 as an exam for us human beings to solve, right? There's no recipe, there's no answer, there's no path, there may not be a clear path to an answer. The way we train our students, the way we evaluate our students is disconnected from problem solving in the real world. I wish young people were exposed to problems that the teacher does not know the answer. That's when we will have real progress in young people's education, because we present an inaccurate view of problem solving when we only train our students with problems that have a definite answer and where someone knows the answer. Cancer is not a problem like that. COVID-19 is not a problem like that. Environmental degradation, environmental issues, it's not a problem with a recipe. So my strong appeal to educators around the world is to say, it's not too early. It's never too early to expose children to problem solving that does not have an exact answer, does not have a known answer. You make progress by working towards an answer. You figure out what doesn't work. Even that is progress when you have open-ended problem solving.
Yeah, I think you are correct. Just as they say, a failure in science is not a failure if it gives you some data.
One of my colleagues said that it's called research. It's not called search. But you don't find it the first time. You keep searching, you keep failing, you keep searching, you keep failing until that's how you make progress.
Yeah, and even in some of the advanced countries, like developed countries, like take in Australia as well. Um, to extend to that question again, like um, I also agree strongly that the next generation, the youngsters, is the only biggest hope that we have currently. And when left without any indoctrination, with the general curiosity, and if we left them with imagination, curiosity, and interest, they will become rationalists by default. But because of the appeasement politics and all, like politicians and leaders, they are systems that we already have established, they continue funding religious studies and teaching irrational things, or subjecting the children to irrational things, like strong faith in in non-materialistic opinions or stories.
Mm-hmm.
But at the same time, like more and more environmentalists, or if we can observe properly, youngsters, like young students, they are coming out and speaking and protesting, or pleading the elders to do something about what's happening with global
That's right.
warming
Greta is
or
a great
climate change.
example, right?
Yeah,
Greta is a great
So-
example. It is absolutely right that children are naturally, they're born curious, they're born creative, they are born problem solvers. Whether it's a human child or some other living thing, children are born with curiosity, they're born with creativity. We just have to stop beating that creativity out of them. We have to stop beating that curiosity out of them. I remember, I literally mean this, right? Beating it out of them. What I mean by this is, we are so strongly discouraged from asking questions in classrooms. I remember being discouraged from asking questions in the classroom. The teacher felt I was challenging their authority by asking a question. That is just the wrong approach to education. When we do that, when we discourage curiosity, when we discourage questions, if it's a genuine question that's well meant to understand something, if we don't encourage it, that is beating curiosity out of our children.
As I say, there is no wrong question.
Yeah.
I read
Such
somewhere
thing
that instead of trying to get your children to learn the right answer, to come up with the right answer, help them to actually encourage them to ask more interesting questions.
Yeah,
that will get them sort of on the right path.
Yeah, there's a big push to what is called experiential learning, where you learn by experiencing something, which is just fantastic. I've seen many fantastic examples of this experiential learning, where you can be told that the Sistine Chapel was painted by Michelangelo while he was lying on the scaffolding, painting above his head. Has a child ever painted with their canvas above their head? No. If they do that, if you're taught to do that, that's better than hearing a story about Michelangelo painting the ceiling of the Sistine Chapel, right? When we want to talk about this, when we want to talk about something, when we want our child to imagine something happening, let's have them experience it. That's just a minor example of something, but experiential learning is something I've become a big believer in. Learning by doing, not learning by hearing, but learning by doing.
Sorry. Yeah, very interesting. So I think we're nearing towards the end of it. So unless Amol or Teja, if you have any more questions for Professor Rajguru.
Well, I guess I have a few sort of questions related to the word cannibalism in the context of in the context of gravitational evolution, because there's generally a very sort of deep meaning in when a word is assigned to a particular in astronomy. So I was just wondering where that word comes from and how relevant, how closely it describes the actual behavior that's happening out there.
So cannibalism means eating your own kind, right? That's what it means. It's an overly dramatic word for what goes on in galaxies, right? Galaxies, if you have a small galaxy, it falls into a big galaxy. After a little while, the small galaxy is really not discernible anymore. Its stars have been, in a way,
Consumed.
eaten, incorporated by the bigger galaxy. That's what, in that sense, cannibalism. It's not violent. It doesn't cause loss of life. In that sense, it's not like, like a human being eating another human being. A good way to think about galaxy cannibalism is like a corporate merger. When you have two companies merging, a company consists of people. When you have a group of people and a company, it means the people's loyalty revolve around a particular goal that that company is associated with. You have another company, a second company, company A, company B. Company B, there's another group of people whose loyalties are around company B. When the two come together and merge, some people are laid off. That's like orphan stars in a galaxy collision. But then at the end of the day, there's a common purpose where there were two sets of purposes and two sets of people, one following purpose A, one following purpose B. So galaxy collisions are more like corporate mergers.
Would you say the large Magellanic Clouds and the small Magellanic Clouds, just essentially satellite galaxies of the Milky Way, are they being eaten by the Milky Way? There's some interaction happening between the galaxies.
They are being eaten by the Milky Way. They're not going down without a fight. They are causing some distortions to the Milky Way. That's one of the things I'm studying with one of my PhD students and a couple of collaborators. The way because galaxies have finite size and because gravity is a distance-dependent force, what happens is the pull of one galaxy on another is not a uniform force at all parts of the galaxy. The near part feels a stronger pull than the far part. That's called tidal effects. We're trying to study the tidal effects of the Large Magellanic Cloud on our Milky Way. Other people study how the Milky Way is trying to disrupt or is in the process of disrupting the Large Magellanic Cloud. It's one of the things I'm using the Keck telescope for. My colleagues and I are using the Keck telescope for later this year. And during those nights, we'll actually host Shadow the Scientist nights, and we'll encourage kids from all around the world to take part to see how we get at a question like this. What is the critical thinking process that leads to that?
I would really be interested in that, sir.
Let's stay in touch. We have a website that's called shadow.ucsc.edu. Very simple, shadow for Shadow the Scientist, .ucsc for UC-Santa-Cruz.edu. And you'll see over there, there's something like 20 different nights listed there the rest of the year, during which we'll be hosting these sessions. And we ask people to sign up. It's a simple Google form to sign up. And when people sign up at the end of this, we haven't put out Google Forms for all the nights because only for the night that's coming up on July 9th, we put a Google form there. But we'll soon have Google Forms for each of the nights as we approach those dates. And when people sign up, they get a Zoom link to take part. It's free to sign up. It doesn't cost anything. It costs your time. It's the only thing it costs. It costs a couple of hours of your time to take part in this.
And as an astrophotographer, I just like to say the dramatic sort of mergers of these galaxies and them colliding in various stages and various phases, the starburst galaxies and then the mice. So that always is the most epic of the photographs. When you understand what's happening there at that scales.
It's like taking a snapshot of fireworks in the sky. Spectacular, absolutely spectacular. Some of the most photogenic things in the universe are colliding galaxies. Beautiful photographs. They're allowed to take beautiful photographs.
I think, Amol, you being in the southern hemisphere, you should feel lucky enough. I think there are at least 7-8 different satellite galaxies that are visible from the southern hemisphere, if I'm not wrong.
Well, the Large Magellanic Cloud and the small they're the ones where easily visible. And half an hour's drive from Sydney.
Yeah, naked eye. You don't even need binoculars, right? Naked eye. This is beautiful. To see another galaxy with our naked eye is otherwise from the northern hemisphere, the most the most distant galaxy you can see is the Andromeda Galaxy. It's about 2.5 million light years away. These things are less. They're more like 100,000 light
160
years.
to 100,000.
Yeah, exactly. A few 100,000 light years away.
And personally, like because as normal people, they are not well connected, or they one is the access of information, and also astronomy as such doesn't affect a normal person's day-to-day life or activities. But as astrophysicists and anybody in space sciences, when they try to uh, understand and know the universe around them, from what happened from the distant past to what is going to happen in the future, like they kind of get to know a lot of questions answered in their life as to where we are coming from and where everything is coming from, and the evolution of not just galaxies and stars, planets, life, and everything around us. Like uh, it- so how joyful is that personally for you, when you know a
Yeah,
lot of things from science, especially in astrophysics physics?
it is a huge source of satisfaction. I think it really affects your perspective as a sentient being when you get to study things that are so much bigger than ourselves in space and time. We started with this question early on. It really affects one's perspective in a big way, in a way that I can barely describe. It's like standing on the edge of a seashore and seeing the vast ocean. It changes who you are. It changes your perspective in that moment when you see something that's so much bigger than yourself. It's different from sitting in a room where what you're seeing, everything is sort of within reach, and when things are so far out of reach, they change your perspective in ways that's difficult for me to describe. I feel very privileged that I get paid a salary to study something as beautiful as the universe. I get up every morning to study something that I absolutely love, and not everyone can get to say that about their job. I feel very privileged that I get to do this.
And at the same time, like given the when the vastness and the lack of lack of control on the things much bigger and farther from us, like um, uh, is there some kind of sadness as well, or some dissatisfaction that we are so helpless on a small speck of dust when compared to the entire universe? Like, are we are not significant enough to
Existential crisis.
yeah.
It is. It makes some people sad. It makes it. I suppose there's a certain sense of how fragile our planet is, how fragile our species is compared to the things out there, how small we are, how insignificant we are. These are not depressing thoughts for me somehow. They are perspective setting, they're mind expanding, but they're not depressing to me. That's my personal perspective. I'm not saddened by the fact that there are things out there that are much bigger than me. I am in fact filled with a sense of privilege that even though physically our heads are small and our brains are even smaller than our heads, that we have the ability to contemplate, theorize about things that are so much bigger than ourselves. That's a sense of privilege, that we are able to consider things that are so much bigger than ourselves. I don't see that as a negative. I see that as a positive.
So science is the only tool, and humans trying to explore and understand what is happening around is the matter getting to know itself. Human mind is one of the most complex and complicated or organ in this entire known universe for us. So what in your opinion, like do you think the possibilities of extraterrestrial life or alien life exist beyond our galaxy or within our galaxy. I know it may not be your primary area of focus, but
No, I mean,
what are your
just
ideas?
by talking to people who have this as their research focus. I have colleagues who study astrobiology, which is thinking about biology beyond the Earth, or people who think about the search for extraterrestrial intelligence. I have close friends who work in these areas. I think that's a super, it's a really important question. Are we alone? Is a question that we've asked through the ages, right? When people explored the dark continent, what was called the dark continent of Africa, it was to find out what else is out there. Are we alone? And the human spirit of exploration is not going to go away soon. It's been there as long as the species has existed. And it's not just a human spirit of exploration. Every living thing explores. In a sense, the search for the possibility of life on other planets and other galaxies is such a natural human instinct. We understand ourselves better when we see others like us. When we travel to another country, to another continent, we don't go there to look for people who are exactly like us, who have had exactly the same life experience as us. In fact, we're enriched by people whose life experiences are different from ours. In the same way, finding planetary systems that have formed that are very different from our solar system is something that's already happening. Exoplanets is a huge field of research. So I think we are taking steps, logical steps, towards understanding, certainly towards understanding our solar system. Planets around other stars is a well-established field now, exoplanets. Understanding the conditions that give rise to life is a next logical step. One of the real challenges is, what diversity might exist within life in the universe. We're used to a very narrow slice of life when we think about life on our planet. It's very difficult for us to envision what kind of, how different life forms could be. We see this in movies all the time. Extraterrestrials are presented in so many different ways in movies. I don't think we've reached the limits of our imagination in understanding, what other living things might look like. It's a fascinating field. It's not something I work in, but it's, as you said, but it's a fascinating field. Natural human instinct.
Yep. I think the research and the results themselves will be a lot more interesting, not just outside the solar system, but within the solar system, where there is a possibility that life can exist, not outside Earth, like some of the satellites for Jupiter and other planets, and maybe on Mars, like whether at some point in past there was a life or situations where life could have been possible. But I think recently there was a news science article I read about some ecosystems themselves were observed some 500 meters below Antarctica, where in a subterranean aquifer, or more than, I think, deeper than that, there were life forms observed. So that gives us some hope as to the possibilities of life, not on the surface of planet,
not of the
but
surface,
maybe.
exactly.
Yeah.
Deep ocean life forms within very otherwise toxic environments, highly sulfurous environments, high temperature environments, hot springs, deep oceans where there's no light, as you say, underground. This helps us expand our idea of the full, helps expand our idea of the diversity of life. I think that is very closely related to life beyond Earth, very closely related, because the bigger the range of environments in which we discover and understand how life thrives or thrived in the past, the more we will learn. As with many things in research, the process of searching is super interesting. The process of searching is super informative. It's not just finding. It's the bright light at the end of the tunnel is life on another planet. But as we go through that tunnel, we'll make lots of discoveries that are within that tunnel itself. We don't have to reach that bright, even before we reach that bright light.
Yeah, I think there should be the reason for studying astronomy and astrophysics as well. I mean, normally, say for example, today we are discussing primarily on the galaxies. So for a normal person, it may not be of interest, but the process itself, of knowing what happened before, and how it is going to, and like that helps people understand or think critically about the possibilities and the different laws of nature, and which they can apply elsewhere, and also makes them better people at helping solve the problems. So unless we have any other questions, so I think we can close there. Thank you, Amol, for joining from Sydney, and thank you, Teja. Thank you, Professor Guha Thakurta, for joining us today and sharing your experience and opinions about many things related to galaxies.
Thank you so much.
We'll definitely meet some other time and continue our interesting discussions on many things related to science. And thank you for your special interest in continuing your efforts in educating more and more youngsters, and helping them think critically, which I think is also the hope forward for all of us, to win the next pandemic that we are challenged with, that is the misinformation and disinformation pandemic. And I thank all the co-hosts and the technical team behind this. So this episode will be uploaded into archived into Indian Humanists YouTube channel. Currently it is going live. And to join the movement to build a culture of science, which is the motto of Science for Society, please also viewers join Science for Society Facebook group. And if you have any other words, sir, you can conclude.
No, I want to thank the technical team behind this that are invisible but make this magic work. We are sitting far apart, physically sitting far apart, but to make this work so smoothly, thank them for it. Thank you. Many thanks to the three of you for asking excellent questions and for being patient with my answers as I meandered my way trying to answer them. But it's been a real pleasure. Thank you very much for hosting me.
The pleasure is all ours, sir. So it's really wonderful.
It's been a real pleasure and a joy, sir, to speak with you.
Thank you.
Thanks, Prasad, for having me.
Thank you, Amol.
Thank you very much, sir. Thank you very much.
Thank you, Teja. Thank you, Prasad. Thanks, Amol.
Thank you.